Hi everyone. So today we're just going to give a bit of a quick rundown on how to present your lab report and your figures and some of the common mistakes that we saw. We're not going to be meeting again for a few weeks, so I don't want you guys to keep making the same mistakes on handing in your lab reports. So the easier we can solve some of these issues, the better. So the first thing I want to start off with is your whole data. So your data, there's a lot of you that presented a graph that kind of looks something like this. Now the problem with a graph that looks like this, it doesn't really tell us anything informative at all. What we have here across the x-axis is number of reps, and then here we have the height for these two different species, dandelion and aster. So really what this graph is showing us is that on these specific reps, which are completely independent from one another, it wasn't as if these reps were conducted right beside each other or anything to that effect. There's absolutely nothing that makes the rep with the aster similar to the rep with the dandelion. So all you've shown is that specific reps, there are differences between the two species, and that doesn't really show us anything at all. And so we need to present this data in a much better way. So the best way to go about doing this is, instead of using the raw data, which is what you presented, use the average of all the information. So now we have the average dandelion height for a disturbed area. So you guys mostly found dandelion in a disturbed area, and you mostly found aster in a grassland area. So the average dandelion in a disturbed area was found to be 10.6 centimeters, for example. We're going to copy and paste that over, and we found that asters are taller. That's great. Now the only thing you need to do is you also need to include your standard error, and I'll explain that in a few minutes. But first, to calculate your standard error, you're going to do standard deviation in Excel, and you select the exact same columns except for not selecting your average, and you're going to get a value that kind of looks like this. You can drag it across as well. So now we have the standard deviations for both of these two populations. But to get the standard error rather than the standard deviation, you have to divide by the square root of the sample population, which in this case will be 10 because we measured 10 different species. So 10. Correct for that. Now we have the two standard errors. So now, your graph is going to look something like this. We're going to make a column graph, and that is what your graph is going to look like. So we're going to probably want to clean this up a little bit. So you want to format your chart area. Or actually, the better way to probably do this is just to copy and paste your data further down. And then we're just going to add the dandelion aster on top. And we're going to insert our column graph. Now we don't need the title, it's not really informative, so we're going to get rid of that, and these lines are kind of unattractive, and we don't also need to tell that it's an average. You're going to explain that it's an average in your figure caption. So on the bottom we're going to put, this would be species type, but another thing that we want to examine here is that even though what we did test was between dandelion and aster, most of your lab reports weren't comparing two different species. What they were comparing were two different habitats. So we're going to put habitats here, and we're actually going to change these two fields to disturbed, and then here is going to be your grassland. And then you're going to infer in your lab report that these are two different species. And the reason why you do it like this is because what you're testing for in your lab report is a difference between two different habitats, and not the difference between two different species, which is a key difference. And here we're going to put in our height, which is height in centimeters. Most of you are using black and white printers, so you're probably going to make it black and white right away. Now it comes a key point. You're going to want to add in error bars, and you need to put error bars because even though we see a difference, grassland being higher than disturbed, the error bars prove to us that these values are truly different. So to do error bars, you're going to go in your chart tools and click layout, click on error bars, and then more error bar options. You're going to click custom and specify value. For your positive, you're going to collect the two values that we calculated earlier. And then for your negative, you're also going to select the two values. Hit OK and close. There you go. There are your two error bars. Now you can take a quick format of them to make them a little bit, we'll make them darker, and then we'll make them a little bit thicker. And those are your error bars. And they show here that there actually is a significant difference. So that's a good graph. That's exactly what I'd kind of want to see in my in a lab report. You're going to want to have your figure caption underneath, In this case, it'd be the difference of the average height in a disturbed species versus and a grassland species. Simple enough. I would be happy with something such as that. So the other bit that we might want to add in is our stats. Now this stats, what I'm about to show you, you can apply to anything. So when you do your stats, you don't look at your averages, you actually look at your entire population. The reason why is the stats actually compare the differences within a population, so the differences within a dandelion, to the differences between populations, that is the difference between within the dandelion versus the distance between the dandelion and the aster. So if the difference between the dandelion within population is less than the difference with the aster, then we have a statistical significance. Now, you guys can actually test this very easily in Excel if some of you are uncomfortable with SPSS or other stats programs. And the way you do that is you can go into your data, and there's a data analysis package. If you don't have that installed, you can install it by going under Excel options, and then there's a whole section here on add-ins, and you find the analysis tool pack. But if you already have it installed, it's right here. We click data analysis. Scroll down, t-test paired for 2 sample means. Perfect, that's exactly what we want. Your first variable is your disturbed habitat, and your second variable is going to be your aster habitat. Now the default is 0.05, which is exactly what we want, and your output range, to make it easier, just put on the same page to make it more visible. I've accidentally selected the text. Perfect. So here's what we get in the end. Now the one value that we actually want to see is this p-value for one tail, and this is what actually shows you whether or not it's significant. So we have a value of 0.016, and now that value is going to be less than 0.05. Sorry, less than 0.05, which means we found statistical significance. Great. So these two populations are indeed statistically significant from one another, and that's exactly what you want to see in terms of testing. When you report this in your lab report, you put your p-value equals 0.016, and you refer to your figure 1, and you're absolutely done. That's all you need to do, and you've completely done your results. Perfect. That's kind of exactly what I was. Now, for those of you who thought instead of doing a correlation, we'll just go quickly over how to do something like that. So imagine for a second that this wasn't dandelion. Instead, it's we'll do height there and then number of leaves. So we're differently. So we're going to ignore all of it. Instead, we're going to plot a scatter plot, just with this data, ignoring the reps. So that's the kind of graph that you'd want to see. You can obviously clean it up, make it darker, probably make these circular, and you can see already that these are kind of clustered. It doesn't really make much sense. So the only way you'd statistically prove this is you go back to your data and data analysis, and there's a correlation test. This is a Pearson's correlation, and your input range is going to be this section here. Output range, yet again, we want to keep it somewhere inside of the sheet just so we can make it visible, and we get a value of negative 0.27. Now, Pearson's correlation can range anywhere between negative 1 and 1. Where we get statistical significance is pretty much anything above 0.60. That means there's actually a strong relationship, or a negative 0.06, which means that the correlation is actually negative. So if any value that's greater than 0.6 is statistically significant. If you get a value of negative 0.5, that's also kind of significant, but not nearly as much. And anything lower than that, you'd probably not consider at all. So between negative 0.5 and negative 0.6, you have a trend, but it's not that significant. Anything greater than negative 0.6 is a very significant trend, and the same is true for the positive values. A negative correlation is simply if you can imagine, a line going down, whereas a positive correlation would be a line going up. Going quickly back, when you're doing differences, so if you also included the forest data in our t-test before, that would be an ANOVA test, and that's conducted exactly the same way, and you'd probably get a p-value exactly the same.